Type 4 keyboard, bought it with my son workstation. Hacked on it till my fingers play well. Was the winner of '95. Me and the guys from Core had a tour street with lots of history. Christian Childs held a little cool. I should've known I'd lose my history. Well, oh, when I look back now, I can see we all.
Welcome everyone to an maybe amazing FPGA live stream. I hope the OpenBSD song is not copyright protected. I hope it's copyleft or so. Yeah, for this to come together, quite some stuff had to be implemented, and it actually took way longer than I wanted. And actually wanted to go home now, but otherwise the hours of debugging would be a little bit, yeah, so much to you. Won't produce some amazing content and open source and open hardware, and then after many hours a day comes to an end. So what you see here and heard here was not only an OpenBSD release song, song 3.6 or 3.7, summer of '95 or something, and coming here from the SD card, so previous projects here playing from the FPGA on the ULX3S board with our, I actually didn't check my own, but audio should be fine, I hope. With the RISC-V, so Claire's Pico RISC-V, with our own firmware here, and now a little bit switched to C++, and for this to work, so this music came from the SD card, previous videos, so many things coming together, all the previous work, our deck here, our own single bit direct stream digital deck, digital analog converter. And this data, previously we had this in the flash, which certainly was not very flexible. This data, as per today now, came from the SD card. So not only did I implement SPI SD card mode, but on top wrote the code to drive this API-wise, and a totally minimal FAT implementation of our from scratch firmware. Only wanted to share this success story. Sometimes this is also what many people do not really quite understand, how much time this takes to debug all the stuff. I actually got a little bit crazy here. I spent literally the last over 1 hour debugging some random noise. First I thought it's my SD controller. I also this is coming through the SD memory, so we're loading this into HiMem 64 megabyte of SDRAM, bursting 16 to 30-bit dual word bursting SDRAM controller. So quite some achievement. Pretty satisfied with the result. And yeah, I probably have to restart Emacs for you to read this at home. Should have probably, yeah, it's a little bit, it was a little bit on the edge to even stream this. So let's change here the font for live streaming for you to see something at home. And you can quickly go through the code. Also, fun fact, the previous SPI code, I was not driving this clock very fast. I had a clock divider of 200 by default, because the SPI SD card, as per previous video, needs to be initialized with between 100 and 400 kilohertz. So I had some system clock to SD card divider of 200, and because this was bloody slow loading all the quite some hefty WAV files there, so this was right now uncompressed WAV file, and this was so bloody slow that I even changed this. So after initialization, so many details of actually getting this to work and then optimizing this a little bit, and for sure to make this real world production ready, we need to optimize the heck out of this, because right now it's a little bit, yeah, just barely works. Let's take a look on this file. Most of the stuff of today is in the firmware. This certainly is better for you to read at home. And so not only right now the code is not amazing, this is proof of concept. So what you see here, except the Claire's Pico RISC-V and Claire's basic enablement here, everything else Verilog hardware design wise and firmware we wrote ourselves, and it's not yet amazing. I want to prototype a little bit. You might wonder, why do we do this crazy stuff here? It's actually my long-term plan of prototyping some modern firmware stuff. So this, I want to get away from good old-fashioned C. So this is starting to use C++, so lightweight, including our GSMP, my friends and mine, GSMP Enginous exact Enginous converter stuff, 2 decades old, nearly 2 decades old vintage code that we also use in exact image for some codecs like BMP and other codecs. So this code, everything could be more amazing. I just want to prototype a little bit around. So the Enginous swapping, for example, we do here now with C++ templates, because 2020, but we will see. This is just, anyway, it's just random prototyping of having some fun with low-level electrons and logic gates. For the FAT stuff, so we have here now some, right now, yes, so this is not the most modern code. Again, I'm just migrating and converting this firmware to a little bit more modern style, and take a look here. So what I've done today is, except logging some SD parameter errors, a little bit more verbose. Again, not the most amazing modern code, just even the FAT code. So just, I will probably tomorrow also make a more dedicated video of how file system stuff works. File system stuff is here, it's just the most minimal stuff, and one little thing I wanted to try out here is not to do the Enginous swapping manually, because usually you would then have all over the place like LE, like LE little endian 32 something host to whatever order. Although this RISC-V is little endian, but just in case. So yeah, this code is a little bit verbose. This is just because this Enginous converter stuff, probably, yeah, reusing our code. It's not too much of a big of a deal. You mostly copy and paste it anyway. So these are the defines. This is just the most minimal defines that I just wrote myself. So this is exactly what I want to try. Of course, proof of concept, neither high performance, nor feature complete, nor error checking, just prototyping a little bit. So this is master boot record partition. Yeah, so we read the partition table ourselves, also a little bit, just the most bare minimum for now. Then here's some FAT BIOS parameter block garbage of good old-fashioned DOS crap. Some FAT boot sector, some FAT FS info we're not using, some directory entry. So I'm parsing here all the data. We also see this if I trigger here S for loading here on the RISC-V serial terminal. Then you see here all the file names. These are this VFAT long file name stuff, so parsing all this stuff. Right now only the root directory, but yeah, proof of concept. And what I wanted to try here is, of course, yeah, again, leave me in the comments below. Of course, you can always make this stuff nicer, but in my opinion, although this is a little bit verbose, maybe this stuff should be much, much shorter, because, yeah, 2 decades old, there you see how your coding style changes. Nowadays, I would like, yeah, maybe LE for little endian or something. But the magic happens here that you do not need to manually byte swap all the stuff for all the little endian fields here. Just the stuff that I want to innovate a little bit over, otherwise not the most amazing C code. Yeah, so then some directory. So yeah, FAT total annoying file system, but probably dedicated tomorrow. So a good old-fashioned 80s FAT directory, and then here's this VFAT, FAT32 long file name overlay stuff. Then some super minimal internal housekeeping. This is our internal FAT structure for now, of course, like totally nothing because prototyping. Then read some clusters. So for this proof of concept stuff, really, well, not complete, just like, again, pure minimum of prototyping this last 4 hours, getting this to work. But yeah, you can in one afternoon write SD code. And yeah, by the way, this is the loading. So yeah, and this is already with a faster clock, by the way. So we are clocking this right now with a clock divider of 3, so some 10. Actually, this should get way more faster, but anyway. So reading some cluster and reading some next cluster and doing some internal stuff. So command read also, yeah, command read from the SD card. Of previous videos, so yeah, so quite some stuff. The firmware is getting larger and larger, and of course next we need to factor this out in nice headers and see where we are getting. So this is the SD code that you've seen in previous videos. Here's some SD commands, and so initializing the SD card in the SPI mode, waiting for idle, and then parsing here is like reading 512 blocks. Also, I implemented a new thing of switching those because these new cards come up with a larger block size for better flash performance of probably 4096 or so bytes. So we switch this also somewhere here of here reset block size to 512 for better fitting our FAT code here. Decoding the partition table, just iterating here over, yeah, reading one block here of reading block 0, and yeah, most minimal prototyping stuff, just what you're doing in your firmware when you bring this stuff up the first time ever. And yeah, now we can read like nice blocks here from this amazing SD card. Iterate here this partition table, not much to see except, again, a little bit trying to modernize this, and maybe another day. Certainly soon I try Clang RISC-V, certainly worth to try out, and maybe eventually Rust. Right now this is a little bit hard-coded, but really the next weeks then we get the next steps of prototyping here, some file system interface stuff and like dynamic overlaying and device creation. Right now I log on the first partition table here and store this first linear block address here in just some, yeah, how you're doing it for proof prototype. Then we read here this SD read in our block that we have here, one block right now in this RISC-V firmware. We read the beginning of this partition and decode here the FAT stuff, here logging some nice stuff. I can also actually comment this out again right now. I've disabled this because this was too bloody slow. So true and true, then you see how much stuff is actually going on. That is probably nicer for you to see at home. SD log true and FAT log true, and then you will see quite some stuff scrolling by. Kill, no, not pulse audio, but UJ proc. If we then load, I hope this is the right one, flash here, I hope this is the right address. If we now trigger the firmware loading here of loading the WAV from the firmware, you will see how much stuff is going on. So now we have the most verbose logging of SD, SPI stuff and FAT parsing stuff, like file allocation table stuff. So as for SD, and there you see how much stuff is actually going on there behind the scene, and yeah, why I'm hiding this. So yeah, this certainly will take forever of logging everything, like every bit on the SPI wire. That certainly is not what you want to do at home. But certainly this is this kind of log print F style firmware debugging, what you do when you try to get all those fields correct. Yeah, then after reading the basic file allocation table stuff, which I will probably make a dedicated video tomorrow to go through all the stuff, then we decode or iterate here through the root directory for all those entries. And yeah, FAT really not a nice file system, garish quality of the 80s. So super annoying to pass basically some magic bits here, and then either it's FAT32 or not. And yeah, right now this only supports FAT32 because yeah, FAT12 and 16 is like, yeah, whatever. Maybe another day. But this is good enough of right now finding here the song of OpenBSD song 6.1 wave, which, yeah, it doesn't store a dot. So we compare here also, it's filled with spaces. Also here, only DOS file systems filled up with spaces. Not the most amazing file system encoding. Anyway, we string and compare here the song 61 wave. And if we find this, then we store the start cluster. Here high and yeah, coming out of our NUnist conversion stuff. So this should just work on PowerPC and MIPS as well. And then if we found this wave file, we iterate here again with the same FAT reading functions of reading each of those cluster, always the next cluster in this linked list, and read this in high mem. In high mem I call here the SD memory of our dual word bursting SDRAM controller here of 64 Mbit goodness. We can, by the way, if you have a comment, I only rush you through because after this too many, and also yeah, there you see this concept of creating like Casey Neistat style content, spending all the time of debugging is like, yeah, probably I could have a camera. Maybe this is more entertaining of head scratching of what the heck is going on, debugging some white noise coming out of there, some wondering and head scratching what is going wrong. Actually, I thought already I lose bits and swap the data in the SDRAM controller. So 1 hour debugging through all the SDRAM controller, verifying all the mem test and back and forth. Like, why the freaking heck do I get a random noise? And yeah, but anyway, a little bit tiny typo there and here. We can, for a quick test, actually check if we can make the clock a little bit faster. Right now oops, it was also wrong. Kill this buffer, so SPI MMC. Right now I switch the divider after the init, so we still init with a clock divider of 200 for this init, and later I switch here to 3. Let's see if 2 also works. It would be mighty fast. And for the firmware, so this is only clock dividing the system 41 probably system clock by 2. Not yet tested this. I think many modern SD cards are good for 25 megahertz, but we for sure should do this dynamically. So later I will make this even nicer. Even nicer meaning doing this on the RISC-V bus here so that we can do this dynamically from the firmware. We have already some magic memory mapped I/O register for deasserting the chip select. Here is some really creative out of bounds encoding situation, and something similar we could do so that the RISC-V firmware can like dynamically choose the clock. Certainly that is what you want to do for detecting the card type and verifying the maximum frequency, because those cards have some bit fields there of ultra high speed clock frequency stuff. So yeah, we should later do this dynamically, but for a quick test, let's see if this works with the clock divider of 2. And yeah, one thing, of course, right now it is loading, which as you see takes somewhat kind of forever. Right now we are loading the WAV file once ahead of time for the simple reason that we could not uninterruptedly stream this to our DAC. We have only a FIFO of 1. Writing to the DAC, the digital analog converter, has a FIFO depth of 1. So that we can, unfortunately, what is happening here now, probably also running here the wrong C-flex here of, that probably should work without runtime, without C++ exception handling and RTTI runtime type information. So the issue is if we read this block, one block or cluster That might be more than one block depending on your FAT file system size. The problem is that this takes really many cycles. So as you see, this takes like 512 or 1024 plus multiplied by bits. So this like 8 bits on the wire on the serial SPI bus. So this would be too long of a latency for the DEC for 44.1 of a thousandth of a second to load the next data. So we certainly need to either have a much longer digital analog converter FIFO or actually make this DMA direct memory access bus mastering or something of fancy stuff. So let's see, does it still, yeah, maybe clock of 2 does maybe not work. I guess that should otherwise output more dots unless we could reset this once, but maybe that is just pushing it. Of course, the SPI was just a low-hanging fruit. Theoretically, we should of course implement native mode, but that was, I did not find as many specifications. I need to check if everything is the simplified documentation of this bloody SD card spec. Certainly not cool that this is not fully open. So I would, yeah, for this native SD mode that is using all the 4 wires there in parallel mode. Did I actually changed? Didn't even wanted this. Let's just do that without loading the resynthesizing and loading the bit stream. Let's give this one more try, but probably this clock is just too. Oh no, it works. It was just some maybe, maybe whatever. Oh, wait a second. Did I? Ah, no, actually, wait a second. We did not permanently flash the bit stream, so this is the clock by 3 actually. So we would actually need to reload the flash. So yeah, probably that is too fast. But we anyway can speed this up by a huge factor, by a factor of at least 4 by using this native SD mode with 4 parallel serial lines. But that is more work, especially as it's, yeah, there is open source code, so even if it's not documented, it should be possible to implement from dissecting other people's code. So streaming this directly without this loading latency, a little bit more of a challenge. We could do this super simple by just extending the FIFO of this DEC so that we can write bundles of 16 or 32 samples and have the DEC buffer this in hardware. That probably should be enough to load a whole cluster, potentially with a clock frequency or the serial clock frequency of this SD card. But certainly this would be only a cheap and low-hanging fruit solution, like a YOLO solution. Even better, of course, would be to implement DMA and stuff like direct memory access, bus mastering access from this DEC and so on, so that we could have this in memory and have the digital analog converter pull this out automatically from the system bus. But such fancy things probably coming there on a later date. For now, I'm already super thrilled that we have HDMI out, like VGA kind of stuff. We have audio out. We have an SD RAM, like 64 megabyte whopping SD capacity, and yeah, a RISC firmware running, and certainly very nice here. The next only thing is peripherals, and you could really already make this really fine vintage and retro gaming machine and other operating system stuff. So yeah, this is how long it takes to load this from the SD card. As you see, quite a while. Also today we have 0 drop frames, so whatever reason this DOCSIS business cable garbage fluctuates as much each and every day. Anyway, I hope you enjoy this progress. I anyway just wanted to give you an update to show you how much work all this is. Otherwise, people always think, can you send me this and can you make me this? Like, yeah, an hour there, 4 hours there. But nonetheless, certainly this code also, now we loaded this, we can, let's unmute this, and or do I have, this should probably play, should probably double check that what we are.
Keyboard, boarded with my son.
But yeah, that's it for today. Basically, leave in the comments below what you think, and don't forget to share, like, and subscribe. And I hope to see you soon for the next videos and live streams to come. Another thing we could easily do is also have this LEDs have some VU meters, and you would see that this is more in action, but plugging this out, just a little proof of working prototype thing. But sometime soon this weekend I certainly have to satisfy the P3 fans as well, so that we have some video and audio and new ISO images for the P3 certainly. So yeah, that's it for today. I hope you enjoyed the song. OpenBSD, go there. Good stuff, not only the music, also the operating system I heard over averagely secure. But that's it for today, and I hope you learned something.